Okay, welcome to OLO5, which is a very brief online presentation looking at the effects of ventilation or breathing at altitude. Now, when we consider altitude, we tend to look at the extreme of altitude, just as a comparison. And that, as you obviously know, is atop Mount Everest. Now, contrary to popular opinion, and by common vernacular, people tend to say that at altitude the air is thinner. Now, what's that actually mean? It's not really wrong, but it's not particularly right either. What does it mean? Well, in fact, proportionally, there's no less oxygen, nor carbon dioxide, nor even nitrogen at Mount Everest. It's just that in terms of describing it as the air being thinner, it's simply saying that there are few gas molecules per unit area at altitude compared to sea level. The proportions of gases are exactly the same, but the total amount of gases per area are significantly lower as we raise altitude. So, for example, looking at the extreme, which is Mount Everest, we see that the total gas pressure of all the molecules in the atmosphere, instead of being 760 millimeters of mercury, which is what we learnt it was at sea level, because there are fewer molecules, the atmospheric pressure atop Mount Everest is 253 millimeters of mercury. Now, you don't have to remember these numbers, obviously, I'm just describing them as examples. Given that we said the proportions of gases are not different, we can simply calculate the partial pressure of the major gas components at this altitude. So if we look at oxygen, 21% of the atmosphere, be it at sea level, be it at top of Mount Everest, whatever, approximately 21% of the atmosphere is oxygen. If the total pressure on top of Mount Everest is 253, 21% of that is 53, so we have a partial pressure of oxygen at Mount Everest of only being 53 millimeters of mercury. This is quite significantly lower, obviously, than the 160 or so millimeters of mercury partial pressure of oxygen you would see at sea level. Similarly, carbon dioxide, less CO2, but because there's so little to start with, this is not a significant reduction. But the partial pressure of CO2 on top of Mount Everest would be 0.1 millimeter mercury, and nitrogen would make up the bulk of the remaining pressures. If that's the partial pressures of gases in the atmosphere at the extreme altitude, Mount Everest, obviously that's going to translate to differences in the body. So we look at alveolar and systemic arterial partial pressures of the major gases, oxygen and carbon dioxide, we see the following. Alveolar partial pressure of oxygen is about 35 millimeters of mercury. Obviously it's going to be less in the atmosphere for exactly the same reasons it is at sea level. And the partial pressure of CO2 in the alveoli, should you be on top of Mount Everest, would drop to 7.5 millimeters of mercury. Because of diffusion and respiration, arterial PO2 would be almost identical. It is slightly less for reasons that we don't really need to go into at the moment. There is some compromise to diffusion capabilities at these extremes of altitude because of blood supply. As I said, we don't need to concentrate too much on that, but the arterial partial pressure, or systemic arterial partial pressure of oxygen, should you be on top of Mount Everest, would be only 28 millimeters of mercury, CO2 roughly the same as the alveoli. The problem is decreased partial pressure of CO2 in arterial blood will lead to decreased hydrogen ion concentration, which will lead to increased pH. So in fact your blood pH would be significantly higher than it would be at sea level. It'd be greater than 7.7. Given the body's sensitivity to pH regulation, this obviously is a physiological challenge to the body. Let's look at the PO2, which is the most obvious change though. Now you've seen this many times, the oxygen hemoglobin dissociation curve that I've taken from Widmeyer 1327, which looks at hemoglobin saturation, or the percentage of hemoglobin that is fully saturated on the y-axis, and the partial pressure of oxygen on the x-axis. Now if we said in the last overhead that the PO2 should you be on top of Mount Everest, is only 35 millimeters of mercury, and the arterial PO2 is even less, closer to 30 millimeters of mercury, what effect would that have on hemoglobin saturation? If we look at our graph, we see that at those low levels of PO2, the percentage of hemoglobin in your body that would be fully saturated would be about 60%. This, again, poses a significant physiological challenge. Now, I could go on and on and on about the components or the consequences of these changes, but I just wanted to set the scene. But in the spirit of true blended learning, Stuart and I found a good article by eminent respiratory physiologist and sometimes tuna fisherman, not John West, who wrote an article on the human responses to extreme altitudes. It's fairly straightforward, it's fairly interesting, at least I found it interesting, and that gives you an idea. I'd like you to read that and explore what happens as a consequence of being exposed to the partial pressures of oxygens and CO2 that we spoke about in the preceding slides. See what happens to the body should you be atop of Mount Everest. This article is uploaded on your LMS, and you'll probably find it next to this online presentation. So I invite you to read the article, have a think about it. Don't get too worried about the detail. It's really just looking at applying your physiological principles that you already know to this extreme situation. So hopefully you'll find it an interesting read.